Okay, so let's take a look at an example using the method of Frobenius to find a series solution. So here's our question here. So it says use the method of Frobenius to obtain at least one series solution about x equals 0. Then, if need be, use reduction of order to find a second solution. So here's our differential equation here. Let's first explain why we can use the method of Frobenius on this guy. So I want to write it so the coefficient in front of the y double prime coefficient function in front here is 1. So let's divide everything by x. So doing that we get, okay, so divide by x to write in the form y double prime plus p of x y prime plus q of x y equals 0. So dividing by x here it'll become y double prime. Dividing by x here will be 2 over x y prime. Dividing by x here become y equals 0. So this would be my p of x guy, and the 1 in front here would be my q of x. So let's note that. Okay, so my p of x would be the 2 over x. My q of x would be the 1. So if I take my x minus 0, or just x multiplied by p, the x will cancel to become 2. And 2 is analytic at x equals 0, because you can think of 2 as a power series. Also, x minus 0 squared times my q here is just 1, will be x squared, and that's also x squared you can think of as a power series. So it's analytic at 0. So hence, x equals 0 is a regular singular point of our differential equation up here. So whenever you have a regular singular point, you can use the method of Frobenius to find at least one series solution. Okay, so now let's start to find the series solution. So I'm going to erase this stuff here now, and we'll start to find our series solution. Okay, since we've shown the point x equals 0 is a regular singular point, then here's our differential equation. So by method of Frobenius, we can find a series solution of the form, so like this. So we have to find what this n is and what this r is. Okay, but in this differential equation, we need the first and second derivatives. So taking derivative of this series, you're going to take the n plus r in front and then subtract 1 from the power. So doing that, we get then. Okay, so I took the power down in front, n plus r, then subtracted 1 from power. And now let's take the second derivative. So second derivative, I'll take the n plus r minus 1 in front and subtract 1 up here. So doing that, we get then. So we get this then. So I took the n plus r minus 1 in front, subtracted 1 from the power. Now let's substitute the series in place of y prime, and y double prime up in differential equation now. So doing that, we get. Okay, so I subbed into the different equations. So there'll be x times y double prime. Y double prime is this guy here, which I've written here. So it'll be x times y double prime right here. Then plus 2 times y prime, so it'll be 2 times my y prime. This is my y prime right here, which I've written here. Then plus x times y, so it'll be x, this is my y right here, this guy, equals 0. Alright, so now I can multiply this x in. So multiplying the x in, it would add 1 to the exponent here, so it become n plus r minus 1. And I can multiply this x in also and add 1 up here. So doing that, we get then. Okay, so multiplying the x in here, you'd add 1, so it'd be n plus r minus 1, which I've done here. I multiply the 2 in here. And multiplying the x in here, add 1 to the power up here. Notice that this guy, the first sum and the second sum have x at the same power. The third one has a different, it's different power on the x. So let's actually factor out the summation from these two, and also factor out what they have in common. So they have n plus r in common. They have an in common. They have x to the n plus r minus 1 in common, and they have the summation in common. So factoring the common stuff out, we get then the following. Okay, so I factor the summation out of these two. That's here. I factor the n plus r out in front here, and a on this side, and the x to the n plus r minus 1 on this side. So this first term would have this one left. And the second term, when you take out the stuff they have in common, just have a 2 left there. And n plus r minus 1 plus 2 would just be n plus r plus 1. So let me change that. Okay, so I've changed that. Now we're going to have to get these powers on the x's to be the same. So we're going to have to change the indices here, make a substitution. I'm out of space here, so let me erase a few things and we'll keep going. Okay, so here's what we have. Now we need to get the powers on the x to be the same. So I'm going to make change the indices here and let n equal k plus 2. That'll lift this one up 2. And over here I'm going to let n equals k. So doing that, then they'll have the same powers on the x's. So let's make that substitution. So in place of n here, I'm going to write k plus 2 here, 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 here. And since n starts at 0 here, if I put 0 here, 0 equal k plus 2 would mean that k would have to be minus 2. So this summation would start at minus 2. Then I'm going to put a k in place of n here, here, and here. So doing that, we get then okay, so making a substitution. So I put k plus 2 in place of n here. So it's going to be k plus 2 plus r. So it'll be k plus r plus 2, I wrote it here. Then putting k plus 2 in place of n here, it'll be k plus 2 plus r plus 1, and 2 plus 1 is 3, so it's going to be then k plus r plus 3 for this guy. Then putting it here, it'll be a of k plus 2, and then it'll be x to the k plus r plus 1 power. And as you mentioned here, it's going to start with k as being minus 2 because n is equal to k plus 2. N starts with 0, so you put 0 there, you'd have 0 equals k plus 2. That means k would have to be negative 2 starting. And over here, putting k in place of n, here, here, and here. So we have this. Now they have the same exponents on the x's. That's good. But there is now a slight complication. This guy starts at minus 2, and this one starts at 0. So this would start at minus 2, minus 1, 0, and so forth. So we have the minus 2 term and the minus 1 term that would be different. That this one would have, that this one would not have. This starts at the 0 term and goes forward. So let's make an observation. So note. Okay, so note, say you have summation k equals minus 2 to infinity of b of k plus 2. So you start at minus 2. So you put minus 2 in place of k. Then you go to minus 1, so you put minus 1 in place of k. Then you go to 0 and above. So you can write that as series k equals 0 to infinity. So we're going to use that trick here. So we're going to have the k minus 2 term and the k minus 1 term, and then 0 to infinity terms here. And now I'm going to think of this whole guy here as the bk plus 2. So doing that, we get then okay, so the thinking of the bk plus 2 is this whole thing. So we're going to put minus 2 into it first. So putting minus 2 here will be minus 2 plus r plus 2, so just be r. And putting minus 2 here, it'll be minus 2 plus r plus 3, so it'll be r plus 1. Putting minus 2 here will be a 0. Putting minus 2 here will be minus 2 plus 1, so it'll be r minus 1. So that's the k minus 2 term, like we have here. Then putting minus 1 in place of k, so minus 1 plus r plus 2, so it's going to be r plus 1. Putting minus 2 in place of k here would be minus 2 plus r plus 3, so it's going to be r, minus 1. Minus 1 plus r plus 3, so it's going to be r plus 2 there. Then putting minus 1 here is going to be a 1. putting minus 1 here, they'll cancel, it'll just be x to the r. Then we'll have the summation starting at 0 going forward for this guy, which I've written here. And we still have to add this guy down here. And the whole thing equals 0. Now these two series start at the same point, 0, and they have x at the same power. So let's factor out the summation and factor out the x. So doing that, we get then okay, so factoring out the summations, so we can write as one summation, and factoring out the x to the k plus r plus 1 power on this side, there'll be this guy left. So it'll be k plus r plus 2 times k plus r plus 3 times a of k plus 2 plus ak left here times your x power, and we still have our guys in front here. So this one comes down, this one comes down. So we're now going to equate coefficients because it has to equal 0. So it means the coefficients in front of all the x's need to equal 0. But this video is getting kind of long, so I'm going to break it into 2 parts. So I'm going to leave it here and we'll continue with part 2 in the next video.